Hello, everyone. My name is Steve Rehse. I'm a professor of physics at the great University of Windsor in Windsor, Ontario, Canada. I am so pleased to have been invited to talk to you all today. And for the next 10 or 15 minutes, I'm just going to introduce the idea of how you can actually use physics to practice 21st century medicine. So let's go ahead and jump right in and see what that exactly means. So first, let me introduce myself just so you know who I am and you know what I'm talking about. I am a professor of physics and I run a biomedical physics lab at the University of Windsor. I am fortunate enough to work with a lot of really talented students, and here are some images of my current research groups. So these are the students who actually do all this lab. And I hope some of you out there are thinking that someday in your future, you're going to be one of these students too, and you're going to get to do all these really cool things. And one of the cool things that we get to do, I just want to introduce my research just a little bit, involves this Mars rover. So this is a picture of what one of the newest rovers on Mars is going to look like. And if you note in this animation, it's actually shooting out some lasers at this rock and analyzing that rock. Well, that's a technique that I use in my lab, not on a rover and not on rocks, but we use this technique called laser-induced breakdown spectroscopy to shoot out lasers, and then we can analyze the sample. If you want to learn more about us, our research group, and the science that we do, when you're done watching this video, you can watch us right here on YouTube. Just go ahead and search for Rehse Lab on the YouTube, and you're going to find this very cool video. It's only 4 minutes long, so well worth your time, that explains what it is that we do in my lab. All right, so let's get back to what we were talking about. As I'm introducing myself, I am in Canada, and most of you are listening from the United States. So I had a question for you. Did you know that not all of Canada is North of America? Most Americans think that Canada is way in the far north and everything is north of America, but that's not exactly true. Let's go ahead and take a look at a map. So here's a picture of the United States and Canada, and I'm going to zoom in on the area that we're talking about, where I'm working and speaking to you from right now. It's down in the southern part of Ontario. Let's zoom in. Now we can start to see, here's the city of Detroit. It's in Southeast Michigan, and here's Ontario. And if we zoom in even further, we're keeping north-south on this map. Look at that. This is north, this is south. The city of Windsor, Ontario, where I'm located, is directly underneath to the south of Detroit. So there are parts of Canada, this is one of the southernmost parts of Canada, that are actually south of the United States. I have to go north to get back up into the United States. The other reason I wanted to show this picture is just to let you know that from 2005 to 2011, I was a professor of physics at Wayne State University, which is right across the Detroit River from where I am now at the Department of Physics at the University of Windsor. And I've been here since 2011. Because we are located right on the Detroit River, we have to acknowledge the land that we share. And the University of Windsor actually sits on the traditional territory of the Three Fires Confederacy of First Nations, which includes the Ojibwa, the Ottawa, and the Potawatomi. And we respect the long-standing relationships with First Nations people in this place, in the 100-mile Windsor-Essex Peninsula and the Straits, Le Detroit of Detroit. So what I wanted to talk to you today is that I wanted to illustrate some of the things that medical physics concerns itself with. And this is a topic that we concentrate on a lot in the Department of Physics at the University of Windsor. And I'm going to do this by talking to you about some of the specific examples of the diagnosis and treatment of cancer, which is really what medical physics primarily concerns itself with. So what is medical physics exactly? Well, in my definition, it's the use of physics ideas, principles, and techniques in medicine. And usually that would be for the treatment of cancer, but not always. But for the most part, that's what we at least start thinking about. And when I talk about physics ideas, principles, and techniques, there's really two main fields that we concern ourselves with. And the first is diagnosis. Before you can treat a cancer or even a disease, you have to find it and you have to know the patient has it. So this is diagnosis. Specifically, can you look inside the body to see diseases and tumors? How are you going to destroy the tumor if you don't even know it's there and if you don't know where it's located and you don't know how big it is? So we need diagnostic imaging to do that. And then once you know where the tumor is, there's treatment. So with radiation, can you shoot beams of radiation into the body to kill, or the more accurate phrase that we like to use is to control that disease and control the growth of those tumors? This is what medical physics concerns itself with, primarily these two areas. Let me give you an example of why physics is so important. So we're going to talk about X-rays. So anything to do with X-rays is physics for sure. Maybe some of you in the audience have been unlucky enough to have a broken bone. In this case, I'm showing a X-ray radiograph of a broken arm. And this is projection radiography, it's called. It's a two-dimensional image. Ouch, that looks like that's going to hurt, that broken bone in the arm. If you had to take a projection X-ray radiograph of the skull, you could do it and it looks something like this. So the detail in the skull is good, but it's very hard to understand where in that image everything is located because the three-dimensional nature of the skull is being compressed onto a two-dimensional image. Everything's on top of each other. It's very hard to know where anything is in there. So although there's some information, that's not a lot of good diagnostic information for a doctor. So what are we going to do about it? Well, medicine is lucky because physicists are smart. We've come up with something called X-ray CT, which stands for computed tomography. This is an X-ray CT machine. It works kind of like a traditional X-ray radiograph, but the patient lays on a bed, and that bed goes into the X-ray CT machine, and the X-ray source and detector actually rotate 360 degrees around the patient. Here's a video that's playing of an X-ray CT machine with the front cover taken off, so you can see the X-ray source and the detector as it would spiral around the patient, who would be lying in the middle of this donut shape. When you do that, and you use some appropriate reconstruction algorithms to get the image out of it, we can convert that kind of okay two-dimensional skull image to an image that looks like this, something that almost approximates three-dimensional imaging using the beautiful detail of X-ray CT. There's other imaging techniques as well that really are all physics measurements. A very important one is called MRI. It stands for magnetic resonance imaging. In MRI, a patient lies inside a very strong magnetic field, and we use ideas from physics and signal processing to be able to have this wonderful soft tissue contrast inside the human body. And in another very physics-based diagnostic technique, it's called positron emission tomography, we actually inject chemicals that emit antimatter inside the body. And that antimatter, which sounds really sci-fi and really is, but when that antimatter reacts and meets up with the matter inside your body, it annihilates and gives off X-rays. And those X-rays can be detected from outside the body. And when that happens, it makes the tumor cells inside your body light up like a Christmas tree. So look at this wonderful, almost 3D image of a patient into which these nuclear medicines have been injected. And you can see all these areas lighting up, and it tells the physician exactly where the tumors would be. A wonderful, very powerful imaging technology. So if diagnostic imaging was one part of medical physics, I said that the other part was treating cancers. And I want to just give you the one example of treating cancer tumors with external X-ray beams. The idea of this is that we use very powerful beams of X-rays to kill these tumors. This is commonly done in a machine called a LINAC, or linear accelerator. And I'm showing pictures of the LINAC here, and here's the whole LINAC suite, including the table where a patient would lie down here. Here's a zoomed in image of a patient lying on the table. And here's the head of the linear accelerator or LINAC machine. And it's got these laser crosshairs, which is telling the machine and the medical physicist exactly where the X-rays are going to be going into this patient. So it can only treat and control and kill the tumor cells, and it'll spare the healthy cells. To make sure that we don't damage any of those healthy tissues, we have to use a whole lot of math and physics and computing to come up with very complicated, sophisticated calculations of the treatment plan. We're not just guessing and randomly shooting in X-ray beams. There's a lot of work that goes into this. This is true science to help the physician treat that tumor, to control that tumor in the best way possible. One other thing that medical physicists work on is, can we come up with new ways of treating cancers? What are going to be the 21st century cancer treatment methods? Well, one thing that we think is showing great potential is the idea of using powerful beams of protons to kill cancers. All right, protons are the nuclei of hydrogen atoms, and they are charged particles, and they're going to be much more effective than the X-ray beams from the linear accelerator at controlling tumors. So here is a schematic of what such a proton accelerator might look like. You'll note the size of it. It's really, really big. For scale, here would be the patient in red laying on the bed. And this very large proton accelerator would be constructed in a building that the patient would be sitting in. So this is just a massive physics experiment, essentially. 21st century medicine, I think, is going to be dominated by physics, and we need a lot of math and physics and engineering to design these things, to build them, to make it happen. So, like I said, medical physics, it's a great thing. You might want to study it. How can you use physics ideas and principles and techniques in the practice of medicine? Do you want to go into diagnostic imaging and be able to look inside the body? Do you want to go into treatment? And do you want to be able to cure people using really advanced 21st century techniques? That choice is up to you. So 21st century medicine is not just about being a doctor or a nurse. You should be thinking STEM, science, technology, engineering, math. Everybody knows that doctors and nurses are involved in medicine, but there's lots more careers in 21st century medicine than you even know about. There are people in medicine who comes from backgrounds in physics and chemistry and engineering and math and biology and computer programming. There's so many great jobs and careers, and they are fascinating and fun, very lucrative, super enjoyable. So it's not just always about being a doctor. We hope some of you out there are going to be thinking, yeah, that sounds interesting. I'm going to start thinking STEM. I think it would be a good idea. You might want to give it a listen. So thanks a lot for listening, everybody. I'm going to hang around after a while. You can put some questions in the chat, or we can talk if you want to unmute yourself, and we'll talk then. So thanks a lot, everybody. I appreciate your time.